Our next speaker is Sir Andre Geim, who will share about the random walk to graphene. Sir Andre, please.
I have to zoom off. It's a shame, but I would love to have your.
Okay, so right, switch of subjects from life scientists to material scientists, and during the next 30-35 minutes, I'll try to tell my story, how, why I'm here and how did I get it. So when someone gets a prestigious prize, especially something like Nobel Prize, there are usually two questions asked: how and why. How, I'll tell you story behind, and why it usually sounds, why this guy, why not myself? So I'll try to explain why not me, but this material, which is called graphene, deserves the Nobel Prize. Hope to persuade you by the end of the talk. My story probably will start in somewhere middle 90s, when I was a young tenured professor in the Netherlands at that time, and getting tenure is kind of relaxing. You just can forget about your rush for publications, you have secured your position in the world, so you can think about something for your soul. And I was thinking about what else can I do? I'm so-called quantum condensed matter physicist. I was doing some very obscure experiments, which I got grants, I got PhD students, projects, but at the same time I start doing something else, like a hobby. And later, those kind of experiments were called Friday night experiments, which comes probably from the fact that on Friday night we had a lot of beers and decided, okay, what else can we do? Something interesting, something outside the well-trodden path. One of the first experiments I have done was using the magnets which we had at that time in the lab. There's nothing spectacular with those magnets. They were pretty high, up to 20 Tesla, but there were many labs in the world who have those magnets, and they consume a lot of energy, cool down with the hot water because its current goes through a copper coil, essentially. People, including myself, usually put some solid-state little things, semiconductors, and studied what happens in high magnetic field and at low temperatures. Rather obscure experiments. I was doing mostly mesoscopic superconductivity at that time, if this tells you something. And I wanted to something easy, something out of normal way of doing things. And the question I asked, what happens with water if we put water in high magnetic fields? It was a random question, but not so random at that time, because I also had some idea what's happening, some background knowledge, what's happening with water in small magnetic field. No time to talk about this one. So I thought, okay, we have those facilities here. Why wouldn't we try to study water in those highest magnetic field, essentially static, available on this planet? So once upon a time, I took literally a bottle of water, pour it inside the magnet, and this is, you know, not the way usually people do with their relatively, or I would say very expensive equipment, pour water on top. And I'm not sure what I expected out of this experiment, and actually why I have done this way. Probably beer were partly to blame. But the result was spectacular. So what you see here is a water ball of the size of a tennis ball, which freely floats in the air, and green, it's a laser light which shines it to be better visible, and those droplets on the wall kissing this ball, and this continues until you switch off the magnetic field. Well, I certainly was rather well educated already at that time, so I certainly didn't believe that I invented an anti-gravity machine. So immediate culprit for this levitation came as diamagnetism, and after half an hour of calculations, I did find out that diamagnetism is enough to explain the phenomena. Diamagnetism is a quite well-known phenomena, 100 years before, discovered, I think, by Kelvin, who noticed that if you have a strong magnet, even permanent magnet, it produces some repulsing force on seemingly non-magnetic substances. We usually attribute magnetism to something like iron, nickel, and those magnets, but you, paper, everything around us, tables, those things which you consider non-magnetic, they're in fact magnetic. So scientifically it was not surprise, but what was surprise really for me was that when next morning I came into the audience, I found out that not the audience, to the lab, and tell my colleagues who professionally was dealing with high magnetic field for since they're essentially PhD studies and about to retire, they didn't believe this. And I have to go back to the lab and show this phenomena to them, and then show other colleagues, and then other colleagues came back to the lab from overseas, want to see this. It was a lot of hype around, and all colleagues came with beautiful ideas what else could be put in those high magnetic fields. So about a couple of weeks later, I was so fed up with those experiments, so I decided that I need to do something and finish with this circus which was going around essentially all the time. And the idea was to put a frog in magnetic field. If everything magnetic, you need to show we are magnetic. My face didn't fit inside the magnet, but the frog did, and I managed to make a short movie of the frog. Probably the hardest experiment I have ever done, because condensed matter physicists I do with things which do not jump and do not stick to my fingers, and frogs are not. So these days, whether it was worthwhile, I got Ig Nobel Prize for this work, and I agreed to accept this Ig Nobel Prize. Could reject, and no one would know, but this. Sometimes I go to a conference, say, American Physical Society meeting or something like that, and people come to me, "Oh, I know you," and I roll my eyes. "I have no idea what graphene is, but your frog." That's kind of happenings, and I particularly cherish the letter I got about 25 years ago. The letter reads, as you see, "I'm 9 years old and I want to become scientist, want to learn how you float the frog." So sweet from the girl from Alaska. So Sometimes random thoughts and random experiments, as I try to persuade you, they do work. So the next random experiment has nothing to do with my condensed matter experience, was Gecka. And I learned from the background how geckos stick to the walls. They don't use glue, they don't use anything like that. So, so their toes covered with tiny, tiny hairs. And if you pull out one of your hair and you touch any surface, there would be a small attraction force, which is called van der Waals force. Sometimes it's mediated by condensation of water, but doesn't matter. It's van der Waals interaction. The force is minute, nanonewton, but 10 nanonewtons, something like that. But geckos learn how to use all their hairs, and there are billions of them on those toes. Each one produces 10 nanonewtons, billions produces 10 newtons, and it's quite enough to keep geckos on those. So the idea was, all right, I'm condensed matter physicist, but this is standard size, what I'm usually doing in my lab, dealing with that. And using the facilities which we had, we created this forest of hairs, which you see they can stick to each other, they stick to other surfaces. The original idea was to make a Gecka glove and put one of the students out of the window with this Gecka glove. Not for the lack of students, but for the lack of the material. It has never happened, but eventually I have to limit myself with this toy model to demonstrate the works. It turned out to be quite prolific paper, a couple of thousand citations, people still trying to do this. I have seen a real person hanging from the ceiling using the same kind as this Gecka tape principle, but unfortunately they who are dealing with this still didn't learn how detach and attach again. There is climbing going around like on this picture, and after a couple of attachments it no longer works. So I gave you an idea what kind of mentality it is doing random experiments. So now coming to the subject of the Nobel Award, it was also originated with kind of an idea how thin graphite can be made. Why graphite? Because this material is relatively easy to split. I also know at the moment that people are interested in carbon materials like carbon nanotubes and so on, and graphite itself interested, but no one managed to make thin films of graphite at that moment. And I thought it would be interesting to see how thin you can make those films. So the idea was essentially the same as ancient Greeks had. You know, they invented the concept of atoms by just saying you divide a stone into two, then in two, then in two, and so on, until you can't divide it into anything further. That's an atom, the smallest particle it is. So we start dividing graphite into smaller pieces using different technique. It didn't work for a few months. My PhD student, whom I gave it idea, did manage to succeed in anything new until we tried a sellotape. So using sellotape, you stick it to the surface of graphite, you peel it off, you have a fresh surface of graphite. Thousands of researchers around the world did this kind of approach, method of cleaning graphite, putting tape on top, peeling it off, throwing the tape away, studying graphite. What they didn't realize, that throwing away the tape, they possibly had thrown their Nobel Prizes as well. So what we did, we look at this tape in a microscope, what I did at some moment, and putting, this is a typical image what you see. If you shine light through, the light goes from behind the screen, and you see on the tape under some magnification there are thick pieces. What thick non-transparent pieces tell you? That material is a metal, it's not transparent. But when you see a metal which is transparent, you immediately get an idea that it's a very, very thin metal. Looking at this, this metal is here. This piece of graphite is only a couple of nanometers thick. And this was kind of Eureka moment for me. I can make graphite really, really thin. So why it was a Eureka moment for me? Because, yeah, education helps. Sometimes you just see something and throw it away without noticing. What I knew, and you know this, and let's learn it together, that things around us in the world where we live are all three-dimensional, have height, width, length, and so on. And why it is so? You won't find anything which is a wire which is one atom thick or a single atom thick sheet. Why? Not because you wouldn't be able to see it, but because things do not go like this in our universe. Because whenever you make a material, to grow this material, one way or another, you have to have temperature. And temperature causes atoms move, vibrate, and so on. And if initially you get something which looks a bit flattish, like you will see somewhere now here, then eventually it's all merges into three-dimensional architecture. Or you can say a different way. The nature try to utilize all three dimensions, and this quenches those violent vibrations which destroy the order. So whatever you try, you can't grow two-dimensional materials which are one atom or one molecule thick. So and this was surprise that we could make those materials which assumed by all those many theorems impossible to produce in our three-dimensional world. But we played a trick with this Scotch tape. Essentially we tried a trick, which is taking three-dimensional material, it's graphite, or you can take any other materials, and imagine that you have very tiny tweezers and you pull an individual atomic plane out of this three-dimensional material. Those theorems, physics theorems, which you can't break during growth, you can still do in this experiment, because what you do, you start with three-dimensional material, which was grown at very high temperature, and then at low temperature, which is relatively low, it's our room temperature, you pull out an individual plane, and there is no theorem that forbids it. But the mentality was not there to do this kind of experiment, and even thick for two-dimensional material. So this is an example of a photograph at that time, about 15 years ago, 1 millimeter monolayer carbon, one monolayer, one atom thick carbon crystal, which is seen here. You can see it by naked eye. Also quite a surprise, because one atom you just think it would be the thinnest possible film you can imagine. You expect it to be completely transparent, still you can visualize. Of course, you can use all these powerful modern techniques, including transmission electron microscopy, and make sure that it's indeed crystal of carbon atoms. And this is real photograph there. Okay, so what? We make those monolayer carbon sheets, extremely thin structure, and one say, so what's so special? It's good, it's nice that we can extract atomic planes, but so what? And if it would be just this trick of extracting atomic planes, it would be probably, I wouldn't be here. It would be just a scientific curiosity. But then over, say, 3-5 years, we start looking at the properties of this material more carefully and found out that it's extremely unusual. It's turned out to be not only the material with the largest surface area, 1 gram covers a few football pitches as we measure surface in Manchester, but this kind of expected from the thickness of the material. What we didn't expect that it turned to be the strongest material, at least in the lab, ever measured. It's not only strong, it's stiffer than diamond, but try to pull diamond or compress diamond, you wouldn't do anything. You would be not able, but this material is pliable, is stretchable, this graphene, very unusual properties. And this shows record thermal conductivity, it's outperforming diamond, and it also carries current 1,000 times per thickness higher than copper or gold or silver can do. And there are plenty of other properties. But what we mostly learn from this example of this material, that if you take one atomic plane out of three-dimensional material, you find out that properties are completely different and unexpectedly different from its parent. Then, from those properties, new science did came along, and I have no time to describe this science. I'll give you a few examples. One probably most important example is what the Nobel Prize was given mostly for electronic properties of graphene. Bear with me for 2 minutes. It's a rather complicated transparency, but I'll try to give you an idea. When we describe materials which are around us, metals and semiconductors, we use so-called Schrödinger equation. It's it's written here. It's just like bullets move with certain mass and so on. But in the world of astrophysicists and particle physicists, when particles move with the speed close to the speed of light, you use another equation, which is called Dirac equation in simplest form. And this is essentially relativistic versus non-relativistic physics. What graphene bring about, it brought mimicry. In our normal world of speeds slower than speed of light, electrons within graphene behave like they behave near neutron stars during the Big Bang, if you wish. So you can now mimic with graphene many experiments which was impossible to mimic before. And this was, for many years, it was the focus of a very large community who were dealing with this. I'll give you one example what what kind of phenomena you can address with graphene. One of those is called Klein tunneling, predicted 80 years ago or something like that. And it's about the following. You know, if you drive your car into the wall, what would happen essentially. If you ever heard about quantum mechanics, you know about phenomena of quantum tunneling. And according to the laws of quantum world, if you drive a quantum car into a barrier, some ghost of this car, depending on the height and thickness of the barrier, would go through. That's what usually physicists are dealing with. But if you live in the world governed by the laws, particles, electrons behave within graphene, then if you if you live in this kind of world according to those laws, then if you make a car and make a barrier, however high or however wide the barrier is, the car can go through without noticing this barrier. This is very important phenomena. It's explained many properties of graphene. One of those is very high conductivity. Essentially, you build a barrier in graphene and the electrons do not notice this barrier. They tunnel through this barrier. So a routine phenomena for graphene, very counterintuitive if you are not a physicist. I'm short of time, so let me skip several other examples of phenomena which we observed over years graphene, and just give you an idea that the search for new phenomena in this material goes on. It's last year example. A simple, rather simple experiment we have done, and it was astonishing. More about chemistry rather than physics. You know what the philosopher's stone is. Philosophers try to find a substance which turns something into gold. So in our case, this something is electronic waste, where your computers, your mobile phones go into this, where that's our rubbish. You put aqua regia, a mixture of two acids, wash realistic this kind of electronic waste, you put it through, you get a liquid, and then you pour this liquid through a collection of graphene flakes. And this is real-time experiment, and you see graphene which was black, plenty of these graphene flakes there, getting yellow and yellow. Then you take this yellow stuff, burn it literally in air, and you get gold, essentially. Yeah, so it's last year experiment. It still remains to be seen whether it would go to industrial production, but it's very efficient way of extracting gold. For me, graphene was dead already 3 years, scientifically speaking, because we knew everything about graphene after 3-5 years. 1,000 people around the world studied this material, so nothing left there. But somehow, as you have seen from the previous example, we're still studying graphene. And the reason for this is this turns out the materials with scientifically incredibly long longevity. Why it is? Because this material reincarnates itself in different kind of subjects. The very first one was quite obvious. A year later, after extracting graphene, we tried the same trick with the Scotch tape or many other materials and showed the world that it's not only graphite can be pulled down to individual atomic planes, but many other materials as well. Now we know hundreds, if not thousands, different materials which can be atomically seen from three-dimensional counterpart to two-dimensional counterpart. Before graphene, no one interested, no one even tried to look through those materials. And imagine when you get hundreds and thousands new materials, people are trying to find interesting and useful properties of those materials as well. What else you can do with graphene? A next probably 3.0 or 4.0 incarnation of graphene. If you have a library of those materials, you can do the following and make by design layered structures and ask yourself what properties would be. How can you use those properties? It's like Lego game, but on atomic scale. You can make materials which nature can't do at all. So we and other people are intensively doing this today. It's including Singapore. Many people are working on these materials, and this is real. This is not cartoon. This is an example of new material on the right, where you can make material by design stick in those atomic planes. The latest one, another incarnation which we insectibly science, and gives you an idea how it's important to change a little bit mentality. That's what we have done previously, 15 years ago, 17 years ago. We extracted graphene and forgot about graphite. Change your mentality. Forget about graphene. Ask yourself the question, what happens behind? And what happens behind is a cavity, one atom or a couple of atoms of thick cavity, essentially two edge dislocations with an empty space. Interesting to study how atoms, how liquids, how gases go through this cavity, what properties would be of confined liquids, gases, and other materials within this cavity. And this is all real. We can do this on the lab using so-called van der Waals technology and put in this kind of spaces, which are usually graphene spaces in between two atomically flat systems. So plenty of stuff still going on. Graphene continues to reincarnate itself in through different sisters and brothers, one atom or one molecule in material. So graphene essentially, during the last 15 days, strongly affected and sometimes reshaped the whole fields in physics, chemistry, and even penetrates these days into life sciences and so on. It's already in many industrial products also. They rarely call graphene, they just improve properties of the material. My last slide is more or less philosophical for the youngest people in this audience, for students, PhD students, and so on, who might sometimes be disappointed how their PhDs and so on work, that everything was studied in physics and in energy. So that's a philosophy goes like this. Take a pencil, draw a line, like here. What this black stuff is flakes of graphene, which comes from the pencil lead, because pencil lead contains a lot of graphite. It's the basis material. You can do this. Take a microscope, look carefully at this pencil trace, and like in Scotch Tape technique, if you have enough patience, and I have done once, you can see thinner and thinner pieces in this pencil trace. And the thinnest one, you can find even graphene about this place. Pencils and graphite known for 700 years. So for 700 years, graphene essentially was under our noses, in front of our eyes, whenever we draw something by the pencil. But it took to 21st century having facilities which we have there to realize that graphene, such a wonder material, is underneath. So that's probably tells us something that we don't know yet everything about our world. Thank you.
Thank you, Sir Andre. We will now have a Q&A session moderated by Prof. Lo Hongyi. Prof. Lo, please.
Thank you, Sir Andre Geim. That was a really inspiring talk. Please, this water.
Yeah, I wonder what to say.
So let's open up the floor for questions. Any question from the audience first? If not, we have a couple of questions from the Slido. There was a question that actually got missing, but the question was, what is your next plan for your Friday night experiment?
We're essentially doing it, these cavities, which are very thin, it came as a Friday night experiment. It's required a change in mentality. You can call this kind of relevant to graphene, but the idea is the same kind of using tricks, trying to find something which is not directly related to your normal line of work, something outside, something which you have never dealt before, like molecular transport and liquids, solids, I have never dealt before. But this kind of experiments are now done because I have facilities. I can do these van der Waals heterostructures, I can do this stacking. So in these Friday night experiments, mentality is the same, but facilities are now based on what I have around, like flying frogs. I wouldn't do this experiment with flying frogs if there would be no magnets around. So now I have this huge range library of two-dimensional materials. I'll try to play with them. The idea is the same, trying to play, doing your work.
Thank you. That's like a playground, isn't it? Question from the floor.
Good afternoon. I'm Chao Yang from the University of Hong Kong, and I'm focused on the environmental engineering using 2D materials. So since the graphene has been discovered for 20 years, and now there are many commercial products in the society or in the industry for battery or some energy storage. So for environmental applications, we also focus on the our lab also focuses on the research study and the commercialization of the graphene for water treatment. So my question is, what's your suggestions for the young researchers for the study of the research and the commercial products respectively for different aspects for study on graphene?
You know, to be honest, I'm not an industrialist or a property developer, so I'm a professor doing mostly physics at the university. So to give you advice how to do commercialization of the products, it's not my area of expertise. So all what I can say, try. We know that two-dimensional materials, especially graphene, nowadays are in many commercial products, hundreds and thousands of them. One has to try kind of adventurous stuff. Don't be a follower, but try, even if you're a follower, try to jump somewhere a little bit away, so from the routine which you suggested to follow. So that's only, be more adventurous in your research. So that's all what I can say. And about commercialization, I can't say much.
Yeah, for the research, my question is, we try to discover new 2D materials or some as inspired by you, the new discovery, new discussion, such as the graphene, such as the biolayer or different 2D materials assembled to the layer for different. So these two different directions. So how about your suggestions or comments on the discover new 2D materials or some new phenomena in the graphene-based materials?
I have a colleague who would answer your question. If I would know what to do, I would do it myself and wouldn't tell you.
Yeah. Okay, thank you.
There are 3 people lining up there for questions. So let's turn over to the other side of the room. Please go ahead.
Thanks a lot for your interesting talk. I'm Vishaka. My question is, will graphene replace the silicon-based electronic industry? How long it will take?
Silicon industry, how long will it take? That's a tough one, huh?
There was a lot of discussion 10, 15 years ago about possibility of what you are saying, replacing silicon. First, it was over-optimistic, always. I never really believed that it's possible because silicon is so wonderful material and it's such a huge trillion-dollar industry. It's very hard to do something. But when other two-dimensional materials came around, they offer a range of properties. Some of those are semiconductors, unlike more or less metallic graphene. So people are still, there are papers in Nature. Recently, Huawei announced that in 5 years they will be doing integrated circuits with graphene, but I don't believe it's a question of 5 years. I think it's a few decades, but many other two-dimensional materials, molybdenum sulfide or other dichalcogenides, they do offer something what silicon can't do. It's much smaller, transparent electronics, which would come eventually, but not in a few years, in a couple of decades. It takes a long time to progress from academia to consumer products. But we're looking at the moment on very simple products and not in semiconductor industry, like paints, like tarmac enhanced by graphene, or concrete saving enormous amount of carbon emissions, something like that. Very simple solutions are based currently. We have to wait for more complex solutions.
Thank you. What's your opinion about mica, 2D mica?
Mica is one of many, yeah. So we also dealt with 2D mica, yeah. It's an interesting material, good, for example, for proton transport through this one. Very hard to make 2D mica in large quantities. If you can make 2D mica sheets like graphene square meters, it would be really interesting for many applications. But as you know, we can only Scotch tape mica these days, but it's an interesting material, but one of dozens of interesting two-dimensional materials.
Thank you for the question. I'm afraid we should give chance to one more question. So we have a minute and a half left. Please go ahead.
Hi, I'm Taya. I was wondering, you told us about your successful Friday night experiments. Could you tell about a failed experiment, or about an experiment where it seems like you're asking kind of very open-ended questions, and where you start experimenting, you're like, okay, well, this isn't really going to go anywhere?
if you explore your Friday night experiment, it leads you to failure. That's pretty much the question. What do you do next?
Yeah, it's a good question, actually. One thing I noticed, and I noticed in my written novel lecture, that you expect, like, you know, in venture capital, people expect now 9 out of 10 projects fail. What turned out with me is that nearly half of these projects, which were starting with simple ideas, brought to something interesting. So the chances of success, which I don't understand, are incredibly high than usual. But of course, it's a random idea, sometimes stupid idea, and stupid ideas must fail. And what you do, that's the hardest question, which actually everyone at a stock market, financial stock markets, knows when to cut losses. And that's really, really hard. And yeah, you tend to carry on, but at certain moment it doesn't work. It's really tough solution. But to cut losses, I sometimes say my PhD students, we need to cut losses. And say, oh, can we measure another month? Yeah, very tough.
That was a great advice. I'm afraid we are just on time to end today's sessions. Thank you again for the very inspiring sharing.
Okay, thank you. Thank you.
Thank you, Sir Andre and Prof. Lu.